All right. Am I audible? Yes. Am I still audible? Good. All right, so let me begin by reviewing where we got to last time. So let me describe the setup. So let K be an algebraically closed field. And X is going to be an algebraic curve that's defined over K. And G is going to be a group scheme over X, which is smooth and affine with connected fibers. And so last time I stated a theorem due to joint work with Dennis Gates-Gorey. So there's a hypothesis. So if the generic fiber of G is semi-simple and simply connected, well, then we can say something about the homotopy type of Bun GX. So specifically, I'm going to choose some prime number L, which is invertible in K, and then we can talk about the QL homotopy groups of this Bun GX. And in the previous lecture, I described how to make a map from this into the hypercohomology of some complex of sheaves that lives on X. The cohomology of X with coefficients in some sheaf that I called f bgx over X. And so what is this sheaf? Well, I didn't tell you how to define it, but I told you the essential property that it has, which is that if you take its stalk at any point little x, then you get a complex whose cohomologies are the homotopy groups of the fiber of BG at that same point. Well, sorry, so the theorem is that there's some natural map that's an isomorphism, and this is a reminder of what F looks like. So at the end of the last lecture, I tried to express something about where this sheaf F comes from. And let me start by saying a few more words about that. So this theorem, a priori, should look a little bit strange. It's saying you have an isomorphism where on the left-hand side you have something that looks like homotopy groups. And on the right-hand side, it's something that comes from the homology of a chain complex. So this is something that you would not expect if you were talking about the homotopy groups of a topological space if you were working integrally. So if, let's say you're in topology, Z is some simply connected topological space. It has higher homotopy groups, which are abelian groups, but there's generally no way to construct a chain complex whose homologies are those homotopy groups. But rationally, you can do this. The rational homotopy groups of a simply connected space can be realized as the homotopy of a chain complex that's canonically associated to that space. So this is one output of Quillen's work on rational homotopy theory. Quillen showed that to any simply connected topological space, you can associate a chain complex, actually a differential graded Lie algebra, whose homologies are the rational homotopy groups of your original space. And in order to construct this sheaf that I'm describing here, this F, what you want to do is mimic Quillen's construction, but in this algebrogeometric setting. That's essentially what goes into defining the sheaf F and to constructing this map that appears in this theorem. And what I would like to do in this lecture is talk about a little of what goes into proving that this map is an isomorphism. So let me just remind you, last time I explained why having an isomorphism like this implies We's conjecture in the function field case. And this is now a geometric statement. It's about algebraic geometry over an algebraically closed field. And as I mentioned last time, when the field is the complex numbers, you can prove this pretty easily using ordinary topological methods. It's essentially an H principle. It's telling you that the moduli space of algebraic G-bundles on a Riemann surface has the same homotopy type as the moduli space of topological G-bundles on that Riemann surface. But you can't really turn that into a proof over a field of characteristic P, which is the case that we're interested in for We's conjecture. So what goes into the proof? I'm not going to be able to explain it in this lecture, but I just want to show you in this lecture how to get your foot in the door. So this is a local to global principle, which tells you that you can understand the homotopy type of a global object, namely the moduli stack of G-bundles, as somehow assembled from local data. And I would like to spend most of the lecture talking about a different local to global principle which articulates that idea. So for that, I want to introduce an object, which I'm going to denote by Ron GX. So let me start by defining it informally. So Ron GX is the set of all triples S, P, gamma, where S contained in X is a finite subset, which is not empty. P is a G-bundle on X. And gamma is a trivialization of P restricted to the complement of this finite set S. So I did not make these brackets big enough. And, well, strictly speaking, I should say I take this up to isomorphism. So let me be a little bit more precise. What sort of object is Ron GX? I'm thinking of Ron GX as a functor from the category of commutative K-algebras to the category of sets. And what I should do is tell you what are the R-valued points of Ron GX. In other words, what is the value of Ron GX on some R? And, well, now I precisely mean what I wrote above. It's the triples S, P, gamma, where now S is a finite set of R-valued points, finite and non-empty, and P is a G-bundle, and now it's on what I'll write as XR, meaning X cross with spec R. And gamma is, again, a trivialization of P restricted to, well, what I get by taking XR, and I'll just write minus S, but what I mean is S is a finite set of R-valued points. So it's a finite set I can think of as maps from spec R into X cross spec R. And I just want to remove the images of those maps from X cross spec R. Okay, and I take these up to isomorphism. Now, so what can you say about this object? Well, first, there's an obvious map from Ron GX to Bun GX. So remember, Bun GX is an algebraic stack, and the R-valued points of Bun GX are the categories of G-bundles on X cross spec R. And so what this construction does is just take a triple, S, comma, P, comma, gamma, and assign to it the G-bundle P. You forget that this bundle has been trivialized away from a finite set, and you also forget what that finite set is. So now Bun GX is an algebraic stack. You need to think of G-bundles on X as forming a category. Ron GX you don't have to think of as a category-valued functor. You can really think of it as a set-valued functor. That's safe in this case because although G-bundles can have non-trivial automorphisms, they can't have non-trivial automorphisms that preserve a trivialization on a dense open set. So the good news is that even though BunGX is a stack, this is just a set-valued functor. But the bad news is BunGX is an algebraic stack, and RonGX isn't an anything. It's not representable by an algebraic variety or an algebraic stack. It's not even a sheaf. So not a sheaf for the Zariski topology, or any other topology you could think of. Now, if that bothers you, you could replace RonGX by its sheafification for your favorite topology, and it's not really important. I mean, you could use that object instead of RonGX in what follows. So this is not a sheaf, it's not an algebraic variety, but nonetheless, it's something for which you can talk about invariants like L-adic cohomology. So you can talk about H star of RonGX with, say, QL coefficients. And it's defined by a formal procedure. So it's defined as a, let's say, as the cohomology of a chain complex that I'll call the L-adic cochains on RonGX, which in turn is a homotopy inverse limit, sometimes written as HOLIM, of chain complexes that compute the L-adic cohomology of spec R over all R-valued points. Well, let's say over all maps from spec R into this RonGX. So this is just defined by some formal procedure, extrapolating from the fact that we know we have this sensible cohomology theory defined on affine schemes. So this is a definition you can make for any functor, but in general, probably not such a great idea. You'll never be able to compute it for a general functor, but you can compute it for this functor. This L-adic cohomology of RonGX turns out to be sensible by virtue of the following. So let me call this a theorem. This map from RonGX to BunGX induces an isomorphism on L-adic cohomology. So its cohomology is the same as the cohomology of an algebraic stack. Maybe this means we've computed it, or maybe not, because after all, the cohomology of BunGX is the kind of thing that we really want to understand. So I like to call this theorem non-abelian Poincare duality. And I'm not going to really explain the reason that I want to give it that name, other than to say there's a way of viewing this as an analog of Poincare duality in this setting where it's sort of Poincare duality on X, which is a smooth projective curve, with coefficients in the non-abelian group G. But I was once told that every mathematics lecture should contain at least one proof. So far, I've given 4.2 lectures with no proofs. So I would like to try to, in this fifth lecture, to insert part of a proof of this theorem. So I'm going to say a few words about how this is proved, and I'm going to be a little bit vague. It's going to be a sketch of a proof. So David Hilbert once said, to live outside the law, one must be honest, and I will try to observe that maxim by making sure that the vague sketch of proof that I give you now is within epsilon of an actual rigorous proof that one can give and that you can find in our paper on this. Okay, so what's the idea? Well, the first idea is that there's an even stronger statement here. So even better, so let me call this map something. Let me call it theta. Theta is what in topology you would call an acyclic quasi-fibration. That means that it's inducing an isomorphism on cohomology because all of the fibers have trivial cohomology, and that's true even for a more general notion of fiber. So what I mean is that if you have any map from, let's say, an affine scheme into Bun-GX, then you can form a fiber product. Let's say, I'll just call that F for fiber. If this is a pullback square, then the map from F to spec R induces an isomorphism on QL cohomology. And it's more or less formal from the way I defined L-adic cohomology by a limit procedure, that if you know this, then you know that the map on the bottom has to induce an isomorphism on L-adic cohomology. So now what's this map from spec R to Bun-GX doing? This is a G-bundle. Corresponds to some G-bundle P on X cross spec R. And now, to simplify the discussion, I want to assume that that G-bundle is the trivial G-bundle. So for simplicity, assume that P is trivial. Well, in that case, this fiber F is just a product of spec R times the fiber of this map theta over the trivial G-bundle. So in that case, so we want to show something about the projection map from spec R cross, let's say, the fiber of theta to spec R. We want to know that this is an isomorphism on L-adic cohomology. And therefore, by some kind of Kunith theorem, I might as well assume that R is K. Right? This is just the projection of a product onto one factor. What we need to show is that the other factor is acyclic. So we want to show that the fiber of theta has trivial L-adic cohomology. So what does the fiber of theta look like? So let me give that a name. So let me call this rat of X comma G. So what is this? Well, by definition, the points of Ron GX are given by finite sets together with a G-bundle and a trivialization of that G-bundle away from that finite set, finite subsets of our curve. Now, when I take the fiber of the map theta, I'm fixing that G-bundle to be the trivial G-bundle. So the data of a point of the fiber is rat X comma G. This is like this collection of pairs S comma gamma, where S contained in X is a non-empty finite set. And gamma is now a map from the complement of S into the group G. So it's like, this is the space of rational maps from X into G. Maps that are defined not necessarily on all of X, but on the complement of a finite set. And the kind of thing that we have to prove in order to prove this non-abelian Poincare duality theorem is that this space of rational maps is contractible. Okay, so let's just do a special case. So I'm going to do a special case, which is not a case that we would want to put into our overall theorem. I want to take G to be GLN. So that's not a semi-simple group scheme, but for this non-abelian Poincare duality statement, it's not important that G is semi-simple and simply connected. This is going to be true also for groups like GLN. So let's talk about the case where G is GLN. So now we can think about rational maps from X into G. It's like some space of n by n matrices of rational functions. Well, let me put this in quotation marks. N by n matrices of rational functions on X with non-vanishing determinant. So let me write down an approximation to this space. So an element here will correspond to an n by n matrix of rational functions. So those rational functions might not be regular everywhere. In fact, they probably won't be. They can have poles along some divisors contained in X. So fix a divisor, D, contained in X, an effective divisor. And now let me consider something that's an honest scheme. In fact, it's actually an affine space. So I want to consider n by n matrices of elements of H naught of X with coefficients in O of D. So n by n matrices of rational functions on X whose poles are no worse than the divisor D. So this is an affine space. Let me call it A sub capital D. It's an affine space of some oh no, capital D is taken. A sub M, capital M. It's an affine space of some dimension that if D is a sufficiently large divisor, you could write down what that dimension was using the Riemann-Roch theorem. So this affine space is contractible, right? It's an affine space. Its L-adic cohomology is the same as the L-adic cohomology of a point. And it's pretty close to something that maps into my space of rational maps. If I have an n by n matrix of rational functions, it looks like it determines a point of rat xg. Well, that's true as long as the determinant of this n by n matrix of functions isn't identically zero as a rational function on X. So let's study that question. So there's a map from this space of n by n matrices with coefficients in H naught of X with coefficients in O of D that takes the determinant of that n by n matrix, and it lands in this vector space H naught of X with coefficients in O of n times D. So this determinant map, note that it's not a linear map. It's a map from one vector space to another, or maybe I should say from one affine space to another, but it's not linear. Okay, but now let's assume that D is sufficiently large that the Riemann-Roch theorem tells us exactly the dimension of this space. We'll know what it is. This is an affine space of dimension 1 plus n times the degree of D minus the genus of our curve. And we have a map from this big affine space whose dimension I don't care about to this smaller affine space. And now I didn't leave myself room here. Let me, what are we interested in? We're interested in the n by n matrices that don't go to zero in this smaller matrix. So let's consider this affine space of dimension m. It maps to this affine space of dimension 1 plus n times the degree of D minus the genus of my curve. And then there's some open subset of A of m consisting of n by n matrices whose determinant is not identically zero. So now I'm regretting not giving this number a name, but I won't use it much. So form a pullback diagram here. Take the complement of the origin in this affine space downstairs. That's some open subset of A of M. And this U is something that actually maps to my space of rational maps from X into G. G in this case is GLN. And now the essential point is what do you expect U to look like in this case? So you've taken an affine space of some large dimension and you've removed the origin. So if this map is generic, you would expect U to be the complement of a subvariety of this affine space here, whose codimension is 1 plus n times the degree of d minus g. In other words, it's something that grows linearly with the degree of the divisor d. So let's just write that. This is an expectation. If this map is sufficiently generic, that the complement of U has codimension 1 plus n times the degree of d minus g. And let's just say that's approximately n times the degree of d. Now, if that expectation was correct, if this does actually have large codimension, then, well, this affine space has trivial cohomology. U won't have trivial cohomology, but it will have trivial cohomology in a large range of degrees, a range of degrees which grows with this codimension. And so U, let's just say, will be highly connected. How highly connected? Well, it depends on how big the divisor D is. The larger you take the divisor D to be, the more connected U will look. And now the idea is this space of rational maps is kind of like a direct limit of all these U's as you make your divisor larger and larger. And that process of making your divisor larger makes U more highly connected, and in the limit you should get something contractible. So this is, let's say, infinitely connected. Okay, so that is a rough idea of what goes into this proof of non-abelian Poincare duality. So now I want to talk about what this has to do with what I started the lecture with. So why is this non-abelian Poincare duality a useful statement for our purposes? So let me introduce another object into the story. So the Ron space of X, which I'll just describe informally. This is the space of non-empty finite subsets S contained in X. So that's an informal description. I already defined this for you. This is just what you get when you take Ron G of X when G is the trivial group. So let's say this is defined to be Ron trivial group of X. Okay, so now let's consider this space Ron G of X, which I said it maps to Bun Gx by this map theta. So a point of Ron Gx is a triple consisting of a finite subset of your curve, a G bundle, and a trivialization away from that finite subset. So that has a map to Bun Gx that I was just talking about, which forgets everything except the G bundle. It also has a map to Ron X, which forgets the G bundle and just remembers S. And I want to think about this correspondence and use it to say something. So let me talk about this second map. Let me call it psi. Now the idea, let me talk a little bit about what the fibers of psi look like. So fix a point, meaning a k-valued point, of Ron X. So a k-valued point of Ron X is a finite subset of my algebraic curve. And I want to take, let's, for simplicity, say that that finite subset has just one point in it. So the set X, I want to think of this as a point of Ron X. And now I want to take the inverse image of this point in Ron Gx. well, let me think of this inverse image as sitting inside Ron GX. I'll give an informal description of it. This is the collection of all pairs, P comma gamma, where P is a G bundle on X, and gamma is a trivialization on the complement of this one point. So this object has a name. So this is what's sometimes called the affine Grassmannian of the group G, or maybe I should emphasize it depends also on a choice of point of your curve. So it's the collection of all G bundles on X which are equipped with the trivialization outside this one point. And the essential point here is that this really depends only on the local behavior of the group G near that point X. It doesn't depend on the global structure of the curve X or the global structure of the group scheme G. So this is let's just say a local object. Now, what would happen if you took a more complicated, let's say you took another point of Ron X, which really corresponded to a finite subset of your curve? Well, you could take the inverse image of that S now, and this is something that, well, I could just write the same thing. It's the set of all pairs P comma gamma, where P is a G bundle, and gamma is a trivialization, but now on X minus S. And now, if you have a G bundle which is equipped with a trivialization outside of a finite set, then to rebuild it, you only have to know what it looks like individually in a small neighborhood of each point in that finite set. And that gives you a description of this fiber, which is related to the description of the fibers over the points corresponding to the individual elements of S. This looks like a product over all the elements of this finite set S of a copy of the affine Grassmannian of G at the point X. So this is a phenomenon of factorization. So terminology you would use sometimes is that this Ron GX, the map from Ron GX to Ron X factorizes, meaning the fiber of this map over a point corresponding to a finite set is a product indexed by that finite set of the fibers over those individual points. So this, let's say, this is a factorization property. So now, what does Ron GX buy us? So we're interested in understanding the cohomology of Bun GX. And that's something that's potentially hard to understand because it involves global information about the way X and G interact. Right? You have to think about G bundles that are defined on your entire curve. And what this object Ron GX does is break up the problem into, in some sense, into things that depend only on the structure of G and X individually. So Ron GX maps via this map psi to Ron X, which doesn't mention G at all. It depends only on the curve X. And the fibers of this map are essentially independent of X. They depend only on the local structure of the group scheme G at the individual points. So the cohomology of Ron GX, well, it's sort of built from local information. Now, the fine print is that, well, let me say it like this. So the cohomology of this Bun GX, which is what we want to understand, can be identified with the cohomology of Ron GX by the theorem I sketched for you earlier. And then this you can think of as the cohomology of the Ron space of X, but now not with constant coefficients, but with coefficients in an L-adic sheaf given by pushing forward the constant sheaf on Ron GX. So let me give this object a name. Let me call it A. So what this is doing, we have this space, Ron X, depending only on X. We have this sheaf on it, And the stalks of that sheaf, in essence, don't depend on the global structure of S. They depend only on G. And you put them together by taking the hypercohomology of Ron X with coefficients in A. Now, the fine print is that that could be complicated because this sheaf A can be sort of globally twisted over the Ron space of X. But if you're interested, as we are, only in numerical information, we're interested in the case where X is defined over the algebraic closure of a finite field, or it's really defined over the finite field itself, and we want to take some trace of Frobenius on this cohomology, then it sort of doesn't matter if A is globally twisted, because it's information that you can extract using trace formulas from just knowing what the individual stalks of A look like. So that's why you might think that this is useful information. Okay, so what does A look like? So let me make an assumption. So assume, for simplicity, that G is everywhere semisimple. So that has consequences. One consequence of that is that this affine Grassmannian, these affine Grassmannians, GER GX, they're almost projective algebraic varieties. This is, let's say, an ind proper variety. For all x in the point in X. So what I mean is it's something that you can write as the direct limit of a sequence of projective algebraic varieties where the transition maps in that sequence are closed embeddings. So it's like an infinite dimensional projective variety. So an example of something like this would be infinite dimensional projective space given by the direct limit of finite dimensional projective spaces. That's a rough model for what these things look like. So the fibers of each of these maps is something that look improper. And in fact, a stronger version of that statement is true. This entire map, psi, from Ron GX to Ron X, it behaves in many respects like it's proper. So I'll put it in quotation marks that it's proper. More precisely, if you take the inverse image of any scheme, then you get something that's a direct limit of projective schemes over it. And a consequence of this is that the proper base change theorem applies when you want to understand what this structure, what this sheaf A looks like. So proper base change tells you that if you're interested in understanding the fiber of, the stalk of this sheaf A at some point of the Ron space, let's say corresponding to a single point of my curve, that what I'm going to see is this is going to look like, it's a chain complex, so maybe I should say the cohomologies of this stalk will look like the cohomologies of this affine Grassmannian GER GX. And more generally, you could take the stalk of A at any point of the Ron space corresponding to a finite subset of your curve, and the fiber of psi over that finite set factors as a product, as I mentioned earlier. So by some kind of Kunith formula, you would expect that the cohomologies here look like a tensor product indexed by the points of S, indexed by the elements of the finite set S of the cohomologies of those affine Grassmannians. So this is a feature that this sheaf A has. So this here is articulating that A is what's called a factorizable sheaf. And what that means roughly is it's a sheaf on the Ron space such that when you take its stalk at a point corresponding to a finite set S, it factors as a tensor product of the stalks associated to the individual elements of S. So now what we're interested in is taking the cohomology of the Ron space with coefficients in this sheaf. And this has a name. So this is what's called the factorization I'm not sure if I should call it factorization homology or cohomology, so I'll say cohomology of X with coefficients in A. And now what I'm saying is that that factorization homology is the object that we're interested in. It's the cohomology of Bun Gx with coefficients with constant coefficients now. Okay, so I'm using this language of factorization homology, which I haven't defined for you, but fortunately Matthew defined it in his talks, sort of. So let me just make a remark. So factorization homology is an invariant that makes sense in topology. In topology, and it's associated to a manifold, to, well, what are called factorization algebras. On manifolds. And this theory of factorization homology recovers Hochschild homology when the manifold is S1. Or, well, it recovers Hochschild homology or topological Hochschild homology or various things depending on what kind of algebras you want to consider on your manifold. So when I'm talking about factorization algebra homology in this talk, I don't mean the topological version. What I mean is an analog of that in the world of algebraic geometry, which essentially is defined in the way that I'm describing. It's defined by taking the cohomology of certain sheaves on the Ron space. So we are doing the analog when S1 is replaced by an algebraic curve. X. Okay, so let me just take this statement here and rewrite it in a heuristic form. So heuristic formulation. So factorization homology, you should think of it as some kind of a continuous tensor product indexed by, in topology, by your manifold, or in algebraic geometry by the algebraic variety that you're working with, in this case X. So a heuristic formulation of this statement, I said before this is really factorization cohomology, so let me dualize a little bit. Heuristic formulation is that you can recover the homology of Bun Gx as a kind of continuous tensor product indexed by the points of X of the homologies of these affine Grassmannians. So let me put this in quotation marks to indicate that to the extent that it's a precise statement, it's the previous statement. That tensor product on the left-hand side is essentially defined to be the dual of this cohomology of Ron G with coefficients in A. So let me just mention what the analog would be in the topological setting, in the setting of Matthew's talk. So the Hochschild homology of an algebra A over K is something that you can think of as a tensor product, some kind of a continuous tensor product indexed by now points of the circle of copies of A. Okay, so, well, let me put this in a box and forget about it because it has nothing to do with what I'm talking about. So this looks a little like something that I said at the end of the second lecture. I said that a heuristic explanation for the mass formula that appears in version of We's conjecture is that it's saying something about the cohomology of Bun Gx factoring as a product of local factors. But that factorization looked a little different from the factorization that I'm talking about now. Actually, I'm now regretting that I wrote this Hochschild homology thing. I want to leave myself space for, so let me rewrite what I had above. So the heuristic statement of this non-abelian Poincare duality is that some kind of continuous tensor product indexed by the points of my curve of the homologies of these affine Grassmannians gives me the homology of all of Bun-G. So this was what we did today. On the other hand, in lecture 2, I stated something that looks a little like this, but it was about the cohomology of Bun-Gx. And it was factoring as some kind of continuous tensor product now where the local factors are the cohomologies of the classifying stacks of the groups that you have by taking the fiber of G at the various points. And, well, neither of those is the thing that I actually used to extract numbers. So in my previous lecture, I stated a different principle that was about the homotopy type of Bun-G, which is that you can recover the L-adic homotopy groups of Bun-Gx, QL, as the hypercohomology of X with coefficients in this sheaf f bgx over X. And then maybe I should say we showed that this statement implies We's conjecture. In other words, this final statement has numerical consequences. So I want to say a little bit about how these statements are related. The proof that we give of We's conjecture proceeds by, well, first we prove the first statement. That's sort of what I did today. And then you prove that the first statement implies the second, and the second statement implies the third, and then from the third you use the Grothendieck-Lefschetz trace formula to deduce We's conjecture, to deduce some equality of numbers. So let me say something about, so this implication was today, this implication was in lecture 4. Let me say something about these middle two implications. So the first of these implications, it comes from some notion of theory of Koszul duality in the setting of factorization algebras. So these maps are in a certain sense dual to one another. So both the homology of the affine Grassmannians and the cohomologies of the BGXs are examples of factorization algebras on X. And these left-hand sides are giving you the factorization homologies of X with coefficients in those two factorization algebras. So those factorization algebras are not the same, but they're related by an operation called Koszul duality. And essentially, this implication comes from the fact that the operation of taking factorization homology carries Koszul duality to duality of vector spaces. So these are just related by vector space duality. So once you understand that, the essence of what you have to do is to check that these factorization algebras actually are Koszul dual to one another. And that involves some interesting geometry, but I won't get into it. The other implication is that once you have this product formula that I described in lecture 4, that you can deduce something about the L-adic homotopy groups of Bun-Gx. And this is essentially formal. This is formal from the definition of this sheaf f bgx over x. So I didn't define for you what the left-hand side of this bottom isomorphism is, but I claim that if I gave you enough information that you understood the definition of it, that this implication would just be immediate from the definitions. This sheaf f is obtained from this factorization algebra up here by a formal procedure that will intertwine factorization homology with ordinary, taking cohomology in the usual sense. So how much time do I have left?
A minute.
I have no material left, so that's perfect. Thank you very much.
So before we take questions, let me quickly warn you that there will be a couple of announcements after we finish with questions. So don't get up right away after that, at that point. Having said that, questions?
Is there some reasonable category of geometric things in which the RAND space and RAND G space live?
I mean, they're functors from commutative rings to sets.
Sorry, let me get back here first. Lots of questions.
There we go. Okay. Motivated by that a little bit, kind of a soft question. Since it's lacking so much geometric structure, what motivated you to choose RAND-GX or look at something like that?
Well, so this object was originally introduced by Ron, I think, but it appeared in the book of Balanton and Grinfeld named after Ron, and there it was used as a device for thinking about a different kind of factorization homology, what they called chiral homology. These ideas eventually came from first extracting from the work of Balanton and Grinfeld some topological version of this theory of chiral homology, what's now called factorization homology, that you do on honest manifolds. And on honest manifolds, this Ron space you can think of as an honest topological space. So if you have a manifold M, you can think about the collection of all finite subsets of M, and there's a natural topology on that. Like you can metrize it by talking about the distance between two finite sets. So that's a sense in which it behaves like an honest geometric object. And maybe I should have given a better answer to the previous question. So the Ron space, it's not an algebraic variety, but you can think of the Ron space of X as a direct limit over the category of finite sets and surjections, where S lives in this category of finite sets and surjections of X to the S. So for any finite set, you can take XS, you can take X to the S, which is it's just a product of S copies of X. It's an honest algebraic variety, and it's a contravariant functor of S. So any map of finite sets gives you a map from X to the S to X to the T, and if your map is surjective, that's even a closed embedding. So you should think of the Ron space as the direct limit of all these powers of X under all these closed embeddings. So this category of finite sets and surjections, it's not a filtered category. So the Ron X is not really it's not an in scheme in the sense of being the direct limit of a sequence of algebraic varieties, but it's pretty close.
More questions? All right. This way.
So I'm just wondering if this result is hopefully part of some larger program in arithmetic over function fields, like in Langlands or something like that, or more just stands on its own.
You tell me.
Okay. Or like applications, and
the Bayes conjecture in the function field case was the intended application.
Okay. There's another question here.
So just a question about definitions. Is the formal definition of this parametrized tensor product the dual of the factorization cohomology of the dual algebra? Is that correct?
I mean, I think, things are finite enough that it won't matter where you put the duals. So, if you might worry about a better thing to do is to make an actual factorization algebra, which is like a pre-dual of what I called A, and take its factorization homology, meaning compactly supported cohomology over the Ron space. But I don't think it will matter.
Is there another question? In the back there.
So I suspect the answer is just going to be to read the paper and the constructions, but if we consider these three isomorphisms on, I suppose, these two projectors here, do similar results hold if we consider substacks of, say, Bun-G and then the analogous substack of the classifying space BG? For instance,
What kind of substack are you thinking of?
well, I can't quite remember what you said the other day, but you were talking about considering principal G bundles that are unramified in some finite set of points and maybe crystalline at the others. But if we restrict this problem to say, I have this stack over a spec of FQ, and I want to consider, say, principal G bundles that are unramified outside of a place V and then crystalline at V. This is going to be some substack of Bun-G. Could I concoct a similar complex of sheaves F?
I mean, these G bundles, G is an algebraic group. So
Right.
the notion of G bundle, it's not something which is ramified or unramified. It's like vector bundles.
Right.
So when I was talking yesterday about things being unramified, I was talking about this sheaf F, which is an L-adic sheaf on X. You can talk about whether it is least at various points.
Okay.
But let me say something not in response to the question that you asked, but let me just note something about these implications. They really kind of go the way that I've indicated, because each one of these theorems needs fewer hypotheses than the next one. So, for example, this middle theorem, this also works for coefficients in ZL. You don't have to work rationally for the middle theorem, although you do for the third theorem. And this top theorem, it works it works integrally. You can take coefficients in ZL, and you also don't really need that the generic fiber is semi-simple and simply connected. That's something that really gets used in the proof of this implication here.
Maybe we can take one more question in the front.
So what are some of the essential conditions on the sheaf A to make it factorizable? So, so you use the proper base change theorem, and the fact that the map phi, the fiber of finite sets, all finite sets are factorizable. Are those like two essential conditions that make the sheaf factorizable?
Okay.
Did
Did you not just answer your question?
Oh, it is? Yeah. But so if you're in a more general situation, so would those two conditions be the thing you want to make your sheaf factorizable?
Okay, so there's two approaches that you could take to this. So one is to put yourself in a situation where Ron GX, or Ron G is really proper over the Ron space. So that's true when G has good reduction, but I'm not sure if you can quite extract this from the literature, but more generally it should be true when G has parahoric reduction. And although you can't always arrange that G is everywhere semi-simple, you can arrange that it's everywhere parahoric. So that's one thing you could do. You could choose G nice enough, and then you will have the proper base change theorem. Another thing you can do, which is what we actually did, is to, if you see a group which has bad reduction at finitely many points, you first apply some blow-up construction to make the reduction really bad at those points, to make it so that the group is like a vector group at those points. And then it turns out that you don't really care what's going on at those points. And so you don't consider things as living on all of X, you just consider a factorization algebra on the complement of that finite set of points. And that works too.
Okay, so if there are further questions, maybe we can take them offline. First, let's thank Jacob once more for his lecture series. And maybe I'll